Steve Sorowitsky, aka Steve Suavek. I want to thank VCF for the opportunity to present my project, and I want to thank you all for coming to listen to it. I'm an electrical engineer for 30 years, and I'm crazy enough to spend my free time in the retro world designing different electronic stuff and writing some firmware. For as long as I remember, actually, my hobby that I enjoy since early teenage years has become my job. So somebody said, if your job is your hobby, then it really work. And I can clearly say it's a case, although it not necessarily comes with the all the money we want to grab, but it's a good life. So I'm glad it happened. So let me go with this. These are just as legal disclaimers.
Do we need to sign?
Okay, I'm in the retro scene for about 6 years. Actively, I'm procuring some vintage computers since COVID, when I was just isolated at home, working from home board as many of us. And the first one was Mega 65, and that just started all the avalanche of fascination on the subject that has been, something I enjoyed back when I was a teenager, back in the 80s. So I'm going to share with you some of my early, connections with electronics. I started pretty early. I remember I was 10. I turned the flashlight into Morse transmitter. It was kind of interesting, but I got suspended at school for this. And then I put together a first detector radio to receive long-wave band range at the age of 12. And I was walking around the school and showing out people I could receive the radio station by connecting a piece of wire to a metal pipe in the school. At the age of 13, I made my first PCB with a small voltage AC to DC regulator, hand-drawing artwork on F4, and etching it with a ferric coating. My parents were not happy because I stand in their house during the process. At 14, I assembled the first real electronic circuit. It was a hobby kit that my uncle bought me. It was a stereo LED view meter, and I hooked it up to my dad's stereo system, and it worked. And this was a defining moment that told me I want to do what I'm doing today. I got my first computer, 800 XL Atari, and instead of spending time gaming like my friends, I coded BASIC until the keyboard broke up. At the age of 15, I got my clapper built for turning on lights, like most of us did, like many of us did. At the same year, I built a discrete LED dial clock, and then nightstand 7-second clock that I had until today. A year later, I built multiple devices using Interseal, ICL 7106, multimeter chip, and I also built this thermometer. I was 17. I built also at that time a digital RC meter. It was based on any 555 timer. Pretty simple, but it worked. It helped me to check out some parts I was pulling out from my parents' stereo and TV until they broke. Next, finally in '87, when I was 18, I built something that my dad said, like, oh, it's going to be a nice addition to our stereo system. It was the TMS 1122 based programmable timer. It was a chip made by Texas Instruments from the late 90s to control appliances at home. And I also handmade enclosure from refabricated blank parts to match my mini stereo system. So what you see on the picture is actual piece that I have since that time. I got my first PC 286 Clown on Christmas of '88 after graduating from high school and being accepted to college. This changed everything and solidified me as a future double. I spent all the free time capturing the design schematics in OrCAD and the PCB in the SmartWork which was a small French program for the 2-layer boards. And I simulated in MATLAB and made PLDs in Tango and Couple. Between this and writing my own database applications later, DBase and Clipper, in the break of the 80s and 90s, for businesses like warehouses, I was in a college, my second year of college, and the hospitals to cover college tuition. I also found the time to learn PC architecture and start designing custom add-ons for my PC286, from simple parallel serial port plugins to ISA cards. I was still building some circuits based on designs from some magazines like Practical Electronics or Elector, German Elector, but many of them has been built from scratch, like those two on the top that you see, the green one and the ISA board. This was my first ISA prototype board based on 8255. It was just a parallel board, universal parallel board that I designed. This was completely homemade in 24 hours. And I have been exhibiting the setup to build such a board in 24 hours 2 years ago here at VCF West. At that time, I did first two commercial projects. One was a ticketing system for a local post office, and the second was a PBX data logger installed with the Panasonic Office PBXs in the local businesses. Just a couple of more ISA cards from that time. After designing everything I planned for ISA bus, I switched to World of Microcontrollers with emphasis on Motorola 6-stage AC11 and Intel 8051 family. Having limited funds, I could not afford tools for development, so I designed and built my own tools. One on the left on the bottom is a in-circuit emulator for 8051-52, and I also built the universal programmer for 8051 family, which was later commercialized. That's why it's in a nice package with a nice label. I even coded my own compiler for 8051 after one day discovering a bug in Kyle 8051 commercial compiler I was using from university. These tools opened a new door for effective and fast development of my first commercial products upon entering the world of adult life, paying bills and paying taxes. After college, I got hired as a technical editor of Polish edition of Practical Electronics for 3 years. During that time, I published a couple of dozens of my own designs in the magazine. Almost all were sold as electronic hobby kits and went on the cover page of the magazine, which you see on the pictures. All these were automatic designs. The interaction with electronics hobby enthusiasts was so much rewarding. Some of them I met years later, went to design careers, and some stayed in academia. In '97, I got hired by one of the largest manufacturers of casino-style gaming machines, typically called slot machines, after successfully reverse engineering a couple of PLD chips for them and then winning the bid and delivering a fully equipped functional prototype of casino video poker, for which I solely designed all of the electronics. Actually, I wrote also a demo program for that machine, which was a video poker game, single deck, and it was supposed to be a demo, but it was accepted by the local gaming board, and actually it was commercialized. At that time, I wasn't aware this was such a big of a deal, being a 25-year-old. And that kind of opportunity happens only sometimes once in a lifetime. It was just, for me as an engineer, it was just another baseline project, just more complex, but attainable with experience and tools I gained in previous years. The keys of that design were, of course, PC, ISA knowledge, and practice, 8052, bare metal coding, and effective computer graphics, animations, that I practiced a lot with my PC286 first computer on the target platform. From there, the sky was the limit. And running company R&D, I assembled a team of talented engineers to develop a series of video slot machine games that has been in operation for a decade across Europe, and even long after my departure. Meanwhile, I focused on delivering new hardware for various gaming solutions much needed in the industry at that time. And I have to say, these were the most exciting times, where I could do both hardware and then do software. Some of these graphics that you see are of course, the professional graphic designer, but they were implemented by me in the code. Again, as a demos, and they ended up in the commercial. Since that time, I designed a handful of high-volume commercial products for the consumer and commercial markets here in the US, like variable speed filter pump for residential swimming pools, intelligent control panel for commercial fryers used in the big fast food chains, automatic groundwater monitoring system. I was also an author of the motherboard for medical grade device. With progressive circuits miniaturization, the PCB became smaller, and having fun from being able to actually see the circuit with your own eyes disappeared. Decreasing clock frequencies demanded, taking special considerations during PCB design. This is where all the transmission line theory that you learn at college comes to play. At the same time, I gained more experience in designing for ENC and debugging EMI problems. I understood why most wedge-style computer systems from back in the 80s and 90s were using these metal shields around. Today, lower circuit voltages mitigate these requirements by designing properly planned and routed PCB. And if you have a chance to work a few years in a PCB manufacturing environment, you learn much more than the college or any book can give you to design for manufacturability. Dealing with the component obsolescence or reverse engineering of customer printed circuit boards from Gerber's or the picture was my daily job for a few years. I was lucky enough to work for one of the major PCB manufacturers here in the United States before China took over. And from that perspective, I think this was one of the most important times in my career when I learned something meaningful that changed the way I design electronics going forward to be manufactured. So I'm going to talk about the replicas. So why replica? Falcon isn't my first replica. Isn't my first rodeo. In 2024, I resurrected my old 1987 project with TMS 1122 programmable timer. What you see on the bottom picture is that replica, replicated with the new modern components and completely, recovered board. Then in 2025, I spent the first 6 months designing a replica of Z80-based computer from Eastern Europe called Cobra One. It was a popular ZX Spectrum alternative from the mid-80s, for which developer community exists and support the platform until today. By the way, last year I was exhibiting this computer here at this very building at VCF West. That show from last year, the VCF show last year, hosting a couple of amazing stands, including Atari Retro, 4050 models and 1632-bit Dream machines, as well as Amiga 40 anniversary event, turned my attention into mainstream retro scene, where Atari had a special place in my heart. I brought back to the table my first stashed Falcon, which still worked after almost 20 years in storage. The task of approaching replica of Falcon didn't seem too long to look hard after buying Atari Falcon 30-field service guide copy, which I obtained from local vendor here, printed copy. And then I actually was amazed to find the Gerber package floating on the internet that was published by one of the Atari community contributors, Christian. And I want to have a big shout out for him for that. I contacted Christian asking him if I can use those Gerbers to engage my project to see if we can do any use out of it. If this Gerbers turned to be no good, there was no backup. There was a backup method to CAD scan the physical board, stripped from components, and to get the Gerbers in the drill file. However, the process was expensive. I quoted this process with local vendor. It was around $4,800 to deliver bare boards, strip boards, and get in exchange the Gerber set and the drill files. So I had two choices, right? I was going to check the Gerbers first from Christian, and then proceed with CAD scan if those guys were going to be, no good. There was also a third way to do it, and that's something I was doing as my work. It was just simply, strip the board, take the pictures, put it to Altium, convert it to Gerbers, and then convert it to, editable artwork with the internal layers just basically designed from scratch. So I started from analyzing the BOM and field service, field service guide, and comparing it to the original schematic printed there. So I had the field service guide, there was a schematic in there, and the BOM there, and I compared both. And I relieved dozens of typos and inconsistencies, and it's not a surprise to me. As being a technical editor in practical electronics, I've seen those typos everywhere on every publication. It's just so many information, the risk of missing something is pretty big. But the good thing was that I had the physical Falcon right on my table, so I could extract some of the components and just measure them. For a few interesting schematic design rabbit holes that I stumbled upon. For example, like repetitive VCC loops. So like there's this inductor on the schematic that's just shorted with the VCC. It's like, what's going on here? But having a practice, I know that back in the day, and it was me myself also using OrCAD, where you could actually have separate power planes marked with the same designator like VCC, and had of course them connected together through inductor or ferrite bead, and there was no like a DRC check for that, so it would just fly through the design checkup. So I suspect that what we really hear are just two separate VCC planes. They just connected with the inductor. And also another thing was that I noticed that there's a lack of and then I noticed some of the designators on the schematic was just unreadable. You just could not read them. And finally, there was some unclear comments on the schematic, like trace width equal 1. That I was actually checking, it was not 1 mil, it was 10 mils, so go figure. The review of the Gerber files revealed interesting things like remote location of the decoupling capacitors for some VCC pins. So for example, in this example, we have this capacitor in the middle, and it has connection to VCC on the top, and then the ground is supposed to go right there to the plane, but instead it goes on a 1-inch trace on the bottom. That defies the purpose of the decoupling. Also, I stumbled upon a really weird thing about those Gerbers that I got. So the top layer Gerber around the combo chip had the top row of that chip, shifted by 1 pin. So that paused me for a week because I thought there's some kind of a stunt that Atari pulled, and they ordered a non-standard, QFP package. So I had to get the physical chip, put it under the microscope with the ability to measure, and just completely measure, the package, and it turned out to be just a standard package. So until today, I don't know why those Gerbers were in that state that had the pin, entire row of pins shifted to the right. It is as if someone wanted to put an Easter egg in that package, and I was hoping that if someone just takes those Gerbers and send them to JLC, make them happen, he won't be able to assemble this board. That's the only explanation. And then, of course, finally, there's one gate on this circuit, U26, that has no routing to or from. And it is still marked in both versions of the schematic in the field service guide. So I wasn't sure what's going on because I checked 3 out of my 4 Falcons that I had at that time. None of them had this routed. So what I did on my board, I put provisions with the means of the surface mount jumpers that I could connect that gate to where it's shown here, or have it disconnected as on the physical board. And then finally, I was analyzing the clock net routing across multiple layers stitched with multiple vias, which is sometimes unfortunate. Next, I decided to start from capturing schematic. I use Ultimate Designer, which is a tool of my choice, as I use it professionally for over 20 years now. And prior to that, I used it as a predecessor, which was ProTel, and even before that, Autotrax in DOS era. So why spend time to learn another tool while being proficient in one that you already have in your home? The field service guide schematic quality isn't particularly a textbook example in design world today, but it was acceptable back in the 80s and 90s. One of the goals for this transfer was to keep drawings organized same way as in the service guide. This way, all those who are familiar with the service guide will appreciate clean and searchable schematic of the Falcon in a new form, easy to use and locate components, net or trace. So the copy of the PDF, the schematic I'm going to publish on GitHub next week, is a searchable PDF. So you can just type a component designator, and it will take you automatically to a component in the schematic, and it will take you also on a PCB where the component is. And it will also show you all the parameters of the component, which is a part number and manufacturer. So I had to retain, with this goal, I had to retain all original parts reference designators and net names. I also had to keep part symbols with pins looking the same way to meet this goal. This meant creating non-standard schematic parts symbols with pins showing exactly in the same location, just like original schematic. Same thing with the net labels. I know this in the original schematic, something I mentioned, some Faraday beads showed it the same VCC. So as I mentioned, this suggested that the design uses multiple separated power planes. And turned out there are 9 distinctive power planes on the Falcon. And they marked them from VCC, VCC2 through VCC9. One of the 13, so once all the 13 pages of schematic were captured, I had to validate it, and without data sheets for 3 custom Atari chips, COMBA, PDAL, and SDMA, it was a not straightforward task because there was no 100% assurance that particular IC pin serves input, output, or I/O. However, in the case of Falcon, I was able to identify this just by analyzing the circuits and determine the signal direction flow. Another significant task was to identify and capture all VCC and ground pins, something that was undocumented on the field service guide drawings. Having more than one original machine motherboard, by that time, it was just a matter of checking physical chip pin connection with power or ground rail on the board. At the end, I was able to identify them all, plus identify a bunch of unused, not connected pins, like in combo chip, for example. And I documented those documented pins on the replica schematic. Altium always had a unique capability to support reverse engineering on the PCB. With the built-in Fantastic tool, which is a part of Altium, you can import Gerbers plus drill file and turn it into editable PCB artwork with identified components and nets with just a few clicks of the button. You can even import photograph of the artwork in JPEG or other graphic format and start from there. Assuming Gerbers are correct, of course, the pictures are correct. And if you have a drill file. You can get a drill file from the picture. And this was the case for those Gerbers for Falcon, right? So there was a Gerbers that was not drill file. So we were stuck there. Like I couldn't generate automatically editable board and have it, ordered in 2 weeks. So I decided there was only way to deal with this was to just manually create one drill file, which means to hand place all the vias and pads on the board. And this wasn't really an easy task. I mean, it was easy, but it took me a while because there's a 400 pads and over 490 vias on the board. I also noticed something interesting looking at the Gerbers. I noticed 2 routing styles. One's standard with a 45-degree angle trace corners, and another style using 90-degree sharp or rounded corners. As if someone added last-minute updates to portions of the circuit around GAL and audio analog I/O section using pen and paper. And I'm saying this because some routing lines were not exactly perpendicular versus overall PCB routing, but slightly off by a few degrees. After Gerbers and recreated manually drill file, Altium was able to create a editable artwork file with nets. However, it was unable to recognize most of the component footprints, probably due to quality of the silk treatment layer Gerber. With that, I had no choice but to generate footprints myself for almost 80 different parts. I included 3D models of the components, just in case I had to check clearance on the Z-axis in the future. It was a substantial task, but I used vastly widely available online 3D model websites like CG Trader or 3D Connection, I believe. Some of those models were paid, some of them were free. After original PCB artwork was ported, I had to look into hard to find parts and decide what to do with these. From all parts, there are two components that required attention. One was Yamaha 3439 that was used on the original board, but is no longer available anywhere. You can't even buy it at Best Electronics anymore. Here I changed the PCB artwork to accommodate popular YM2149 derivative, which is used in Atari ST computers, and is just in abundance across eBay and AliExpress. With that, I removed the original footprint from the design. Also, I had to tackle the DSP chip, which Atari ordered from Motorola in a specific non-standard QFP 80 package, which was never available to buy just off the shelf. So the second-hand market for this is not existent. With abundance of alternative packages like QFP 132, which, by the way, I just saw soldered to those Sparrow boards that you've been so kind to bring over to me. There was no brainer just to use those widely available QFP 32 packages and create some kind of mezzanine here, support for mezzanine boards where I could solder, I could create an additional mezzanine PCB and have the bigger package solder on it, and then basically plug into this row of headers around the original DSP that you see on the picture here. And for the big Atari chipset, Trio, Video Combo SDMA, plus the CPU and the supplies still exist, and they can be purchased today from a couple of US vendors. All other parts can be purchased between DigiKey or Mauser and eBay, because I crossed every little part whenever I could. This was also my job for the living, so it wasn't too difficult to do. And the Git repository will contain detailed bill of materials with all the parts brought up to date, the sources which I proved samples from. One important modification that I did to a replica was adding 15-pin D-sub connector, replacing obsolete modulator, RF modulator, which allows connecting VGA monitor ReFalcon without meter for the DB23 adapter. I also added an additional header that is providing connection to VIDA digital signals, RGB, synchronization, and pixel clock. This is everything you need to design decent scaler. What does it mean? It means that it opens opportunity for the community to design video scatter to enable DVI or HDMI compatible output for the replica. Then I look at this clock signal path. I had to fix it because I heard so many stories about this clock. It's like many solutions out there, so I had to tackle this. So the original clock path signal path goes through multiple layers, across multiple gears. There are a total 7 receivers of this clock signal that is sourced solely by a single combo output. Initially, it gets split into 3 branches, A, B, C. One branch feeds FPU and SDMA, second branch feeds CPU and 3 DALs, and finally, one feeds expansion connector, J16. So, with the 7 receivers, it's a pretty substantial load, and without knowing documented combo clock output driver capability, I was not sure how much design margin has left for driving the clock, and I was not sure what this may not be causing the problem. There was also aspect of signal propagation, including unwanted effects of transmission line imbalance. They implemented an original machine multi-drop clock feed was at that time a good solution, but today it can be improved. So without going too deep in a rabbit hole and having tons of other tasks to do around replica, I decided to tackle the issue initially by doing 2 things. One thing was to implement impedance routing for the clock signal path, 50 ohm, and single-ended, which is compromised between lowest attenuation and highest signal capacity, and also separate clock feeds for each of the loads, so they do not affect each other during operation. For the A, for the first one, I had to add an extra copper layer where I could route clock paths keeping 50 ohm control impedance. With Falcon already having 6-layer PCB, that would mean adding another layer number 7, or even layer number 8, if one extra ground plane added to keep board costs low, with symmetrical boards stuck up being mainstream versus non-symmetrical, which were always custom made and more expensive. Basically, the 2 vendors from China quoted me. They said like 7-layer board is going to cost you more than 8-layer board. Before I designed the board, the stack-up for the board, I vetted a couple of popular overseas vendors to see what kind of standard stack-up they carry. This is standard design process at my workplaces, where we don't design our own, what we think is what we want, and then go out to PCBWay and ask for the stack-up because it costs money. We go instead there and ask what they have and then adopt it to our design. That keeps the cost low. So at the same time, I quoted 2 things. I quoted the 8/6 versus 8-layer cost and the 7/8 layer. And it turned out to be that the difference between 6-layer board and 8-layer board was only 10%. So it wasn't too much. It was around $25. So I went for the 8-layer board. And the vendor had a handful of stack-ups that were worth to check. I plugged all of them into Altium, and immediately I got the routing parameters, which is the trace width, and I could just implement in the clock routing. To meet the second requirement, to split the signal, I had to find a component that would serve clock splitting without introduction of too much of the delay to clock signal, and small as too possible. Quick search in the DigiKey browser revealed a handful of candidates, from which I selected one with Texas Instruments, part number CDC 341, which had a very low 4 nanosecond propagation time and half nanosecond skew. The splitter had 8 outputs, so I assigned the following: SDMA, FPU, CPU, 4 gals, and the bus expansion. Paired with the 50 ohm impedance matching resistors, this was a good baseline for future adjustment. Calculating exact values of these resistors was difficult due to lack of information about input impedance of the custom chips. I assumed typical CMOS input impedance of hundreds of kilo ohms just to be modest. Here's a control impedance layer with clock signal routing. It's a kind of star. I'm not sure if it's clear now, probably not, but the clock chip is in the middle, and then there's like a star routing. They're very thin. They're like less than 5 mils. So hard to see. But you're going to see it on the Gerbers next week. So the very first prototype I ordered around beginning of December last year was made by GFC, and the minimum order was batch of 5. And two of the replicas that you see outside are 2 out of this 5. I assembled, I added assembly service to place all SMT passives on the bottom of the board because there were over 500 passives on the bottom board, so it would be a daunting job to put them, hand place them. I was hoping the board to arrive by Christmas, but it made just a few days later before New Year's Eve. So after signing to check for possible shorts between VCC and ground, a few other critical signal path checks, I sent word to my friend, skilled technician, who completed the top SMT assembly, including Atari chipset. Finally, assembling through holes completed the task. First power on resulted in a dark screen. I was very sad, which did not surprise me, considering the complexity of this board and gaps in the communication I had to deal with during porting design to Altium. The culprit was a soldered side of one of the U43 chips, 74HC244, which was used by the system to determine its configuration, like floppy drive type and DMA sound, and also through a U47 SMT jumper array. After soldering those pins, I got the boot screen. I was super happy. ReFalcon booted to basic tasks, and I confirmed keyboard and mouse to be working just fine. Later, after also using test cartridge. With that, I started to do basic tests, hooking up floppy drive first and also using Falcon All30 service coverage I purchased from, I think from Best. Floppy was fine, allowing me to load programs without ID storage hooked up yet. Next, I plugged in 2 GB compact flash card, the adapter, and using multiple floppy HDD driver I purchased to partition and format the driver was successful. The test of the SCSI port using my proven SCSI dongle resulted in failure. The culprit was misfired SCSI port. The connector pin 48 that I pointed here with the arrow was wired to a wrong net, was wired to CD data 0 net instead of just CD net. And the way it happened was actually related to auto-completion when typing a label. So minutes ago, I was capturing schematic circuit around U7, the chip on the left, where CD data 730 bus is present. Then, when labeling SCSI J6 connector pin 48, Altium graciously completed the CD label with adding ATA0, which resulted with a CD ATA0. So I connected physical external pin to a bus. So thank you Altium for that. I missed that during review, but with 1,078 nets in this design, it's very likely to happen. Fixing net on the physical PCB solved the issue, and SCSI worked fine since then. When bringing up the sound output, I noticed garbled noise on the headphones and speakers output instead of proper sound. So the culprit was underpowered audio codec U28 due to a typo in R135 value during porting. So it was supposed to be 4.7 ohm, and I got the type 4.7K. So obviously there was no enough power for the chip. Changing resistor fixed the problem. From there, all remaining tests went well, including MIDI ports, which I tested with a couple of devices, including Roland JDXI synthesizer and Roland MIDI sound module SE55, DSP port with a loopback dongle and cartridge port, as well as Steinberg Falcon digital interface, analog mic line input recording samples, the Digitape software package I purchased, where I successfully captured audio samples to play with them later. I was so amazed at the quality is indistinguishable. I wish I had the Falcon back in '92, because my PC could never do that. Parallel port by printing old school on my NX24-15 star printer. Finally, 2 expanded joy controllers ports on the side of the Falcon. These were a bit of a challenge, but after obtaining Jaguar controller, I was able to confirm operation of the digital portion of the interface. For the XY paddle analog portion of that interface, I was unable to find a single game that would take advantage of these inputs. So community help in validating these circuits is welcome. Although I did do a physical check on the NE556 timers on the physical board that are analog to PWM converters to reacting to a resistance change on the input of the pedal to produce accordingly the proper PWM frequency. So I assume they work. We just need to have it tested with some software. The only port I have not tested yet is a mini-D port used supposedly for Apple Talk. This is a plan to write a sample app to try sending data via this port between 2 computers to convert. It's an RS422 differential RxTX with a handshaking interface, so that should be not too difficult to do. I welcome community to take upon this task. Further testing included very cool Mandela Pro fractal program from '92 to test FPU and DSP by Brainstorm, Digitape audio recording, I mentioned playback up to 32K sampling rate, Jambench by Access, various demos and games, including Famous Joy by NewBeat, and I even plugged in the CT60 accelerator and played Duke Nukem without problems. Most of these tests are reported in social media like Facebook and on my YouTube channel in the form of shorts and videos. So there's some statistics of the board. So there are 820 components on the board. The top has 326. It's a mixed through-hole and surface mount. And the bottom has 502. There are 1,078 nets, over 4,400 pads, 2,400 VS, 65,000 tracks after optimization. The board area is 1,000 1,040 centimeters square, and the population density is not that great, but routing density is huge. I don't even know how much is that. So I'm going to post the files on the GitHub next week. I was supposed to do it yesterday, which, by the way, was my birthday, but
Happy
was just
birthday!
Thank you so much.
Wow.
But I just, between the show, I just couldn't do it. I do want to post something that is still not 100% checked. So this concludes the motherboard, and I just want to mention about one more thing. Having a problem with one of my Falcon keyboards and not being happy after replacing silicon domes with new old stock one, I decided to fix the keyboard issue once and for all. So during the break in the Falcon project, I just sat down and I designed the board, drop-in replacement board for the Falcon. I laid out the board from the scratch based on the looks like hand-drawn schematic that was floating on the internet, not being sure if it's right, if it's correct. And you can see that board on my table. This was again made with the drop-in replacement compatibility. Because I'm a big fan of lighting, I added fully addressable RGB strip, not a strip, but discrete LEDs. Backlight for each MX switch is an option. And I also added 43 individual RGB LEDs on the bottom of the keyboard. So if someone wants more light underneath to light up the translucent case, like I'm showing, you can control this separately. The biggest challenge with the keyboard turned to be the sourcing the keycaps. Obviously, the original keycaps do not support MX switches, so you just can't use them. Thankfully, there's one guy in Poland, Mariusz, who has years of experience in obviously printing, SLA printing, some custom keycaps for different vintage computers, and he helped me out with this. So I ordered a set of those keycaps, milky keycaps from him that you see on the stand. And he printed them, I wrote them, sent them back here, and they're just perfect. I had to UV print the labels because they were black. Typing on this MX switch-based keyboard for me was like a new quality, and I'm going to leave one original Falcon with me, and I'm going to just have the keyboard replaced with this one because it's absolutely perfect. It feels like I can type forever without getting my fingers tired. And I do mostly use the productivity software, which sounds a little crazy today. I rather the gaming, but I encourage you to try it. So this is just a picture of when I was placing the keycaps of the printing. They were a bit yellow, but because the UV light from the printer made them yellow, but then they light up and they become white again. So what's next? Maybe a couple of months vacation. So the replica isn't really end of line for me because again, Falcon is a special place in my heart, and I'm thinking about having one more spin for the science to do where I'd like to do a couple of things. One thing is to embed 16 meg RAM into the motherboard. Why use those modules where those DRAMs are just abundance in China? You can just ask them to populate them for like a couple of bucks. Embed RTC, that is always hard to kind of deal with a proper battery. Socket 68030, I even thought about that, and separate clock, so to do some tinkering and experimentation with overclocking. That would also mean I have to relay out all the buses to do a length matching and control impedance, because right now it will not go very much high, it will just hold. Altium has the signal integrity simulator, so I can very easily verify design and make it right. I also plan to replace hard-to-find GALs that are becoming kind of rare, and mentioned already to relay out the bus. So that's kind of for next year. It's a low-hanging fruit. Make another 5 boards just to see how they perform, if there's an improvement. What next? Then I thought like my ultimate goal would be like put a dual processor configuration where to keep 30 for old software and then having something quicker, faster. Basically embed accelerator on this board, and there is a space for it. After I optimize this layout, there's enough space to put it. So put faster socket CPU, flash, SDRAM, and to complement the TTRAM, and eliminating GALs with the CPLD, and also utilize my long-tabled VGA51 project, which is custom FPGA-based graphics adapter with accelerator that I developed back in 2016 for multi-platform support from 8-bit to 32-bit systems. So it's a single chip, basically like a graphic chip, that you can plug into, configure, plug into any 8 to 32-bit system and get VGA resolution into 56 colors, and you can have sprites and you can have hardware cursor. You can learn more about it in the special website project. It's 8051 Labs. That's like my hobby project website that is displayed on the barcode on the background. So I want to thank you very much, for listening to my short presentation. I want to say a big thank you for all project page backup supporters who got me a coffee or lunch. Viking, Arthur, Peter, Wolfram, Frank, Yanko, Rena, Luke, Ashley, Springfield, Patrick. Big shout outs to Christian Chets. He's a guy who delivered the Gerbers micro, which supported me very much spiritually to start the project, engage it. John, Gilbert, Aaron, and Matt in exhibit support. Thank you so much for that. For project support in media, I want to thank Kunz, Cass, Mercat, Gigi Ferreira, Kroll, Laird, and Götterfinger for covering the project in their YouTube videos. And I want to thank so much to all Atari Forum, ReFalcon thread members, and FO30 Discord server members for a huge thank you for all your ideas and support. And thank you to almost 2,000 project followers between Facebook and X. And finally, huge credit to Monica, my wife, who supported me during this project. Thank you. Any questions?
I'm wondering if you envision having a fully assembled, completed Falcon that you could just sell to people who want your new Falcon.
Yes, that's a good question. I get it from many people. And so I do not have, I'm not Atari, I don't have the license to do it. This design of the board is still copyrighted according to US law. It's like 95 years from publication, so we're still on the road. I got advised just to publish it, and I never meant to make it a business because you can make any business out of it because you're just going to lose money. It's expensive board still today, but if someone would like to have that, I can definitely help to troubleshoot, debug, but everyone will have to take upon himself to get the purpose and make a board for himself and take responsibility. But I'll be happy to help every single time to bring it up. I'm always here to support the community. I would love to see, more people than just 3 right now, 2 testers and myself that could enjoy that board and tinker. Yes.
Thanks. I really enjoyed seeing all the nuts and bolts of what it takes to revive the old PCB. In your assessment, would ChatGPT-like tools have? I saw that you did explicitly call out that. Do you think those would have helped any specific part of what you did?
Very good question. So I did use ChatGPT to check the spelling and grammar of some of my texts. Right, but I'm just an old school guy, and I have enough experience and knowledge to do it myself without ChatGPT. I do have a very frequent conversation with ChatGPT. In fact, I was very surprised that he's able to recognize me as a Falcon guy behind the Falcon. Even if I do incognito mode, we will talk with him. He always starts to diverting and calling me like if you think about your replica to do that, then we'll do this. So it's interesting. It got some traction, but what I want to say is that there are very interesting tools out there. I have a friend in Warsaw. He works for the university. university employee, and he is a very smart person, he machine learning. So I saw him writing a script for KiCad recently that basically took a picture of Atari 130 XL, just a picture of strip board, and in 30 seconds turning this into editable KiCad design. 30 seconds. I have no authorization to show that video to you, but I can send you a link. It is unbelievable. You can see with your own eyes that happening. From the picture, which is really average quality, to just sharp image with the holes, drills, identified PS, past everything. So yeah, the tools are there. It's just, yes, I'm sure we can do it faster now. But again, I'm not an expert in this, so thank you for asking.
So I went online and started looking at the chips. So there are 4 chips that we need to procure to assemble this system, right?
Yes, there are three chips, right? VL combo SDMA that again are sold by a local vendor here in San Jose. Yeah, you need each one of each, so one chipset for the board.
Yeah, I went online and I didn't saw on the website, but I will search that.
Yeah.
But all the other ones are already available on DigiKey and Mouser.
And the second-hand market, which is eBay, right? So like the CPU, you can buy CPU on eBay. Right? You can buy all these obsolete controllers, like SCSI controller, serial controller, LED controller. You can buy between local vendors, San Jose, or the eBay. Yes, and then like 90% of other pods, passives, all the other things you can buy between Mouser and DigiKey, and of course in Europe there'll be equivalent vendors. So I did an effort to cross all the components as much as I could. Thank you. Okay. There are no other questions. Thank you again for listening. I appreciate the comments.